Hello students, in today's class we will continue the chapter Motion in a Plane. In this chapter we will continue some concepts like uniform circular motion, angular displacement, angular velocity, angular acceleration, and the derivation of the relation between linear velocity and angular velocity, and will understand the centripetal acceleration and will derive the expression for centripetal acceleration. Let's understand the uniform circular motion. As you all are familiar with this uniform circular motion, that is the motion of a body along a circular path with a constant speed is called uniform circular motion. Example for this uniform circular motion is that motion of a satellite around the planet and the motion of electron around the nucleus. These are all the uniform circular motion. Next, we will define angular displacement. The angle made by the particle moving along a circular path in a given interval of time is called angular displacement. So, theta be the angle and that is the angular displacement, which is equal to the length of an arc. You can see in the diagram AB is an arc. We take it as S. So, divided by, we will take the radius, that is OA. So theta is equal to S by R, or we can say that length of an arc AB divided by the radius. Let's understand the angular velocity. The ratio of angular displacement to the time interval is called as angular velocity. That is, if theta is the angular displacement in time t, then angular velocity, we will write it as omega, and is given by omega is equal to theta, that is angular displacement divided by time. Next, we will understand angular acceleration. The rate of change of angular velocity is called as angular acceleration. So, we can say that if the angular velocity of a particle changes from omega naught to omega in time t, then its angular acceleration, we will write it for alpha, which is given by alpha is equal to, that is the rate of change of velocity, that is omega minus omega naught divided by t, that is in time t. So this is angular acceleration. Let's derive the relation between linear velocity and angular velocity. For this, let us consider a particle moving along a circle of radius r. Let ds be the very small linear displacement in a very small time dt. So, the instantaneous linear velocity is given by v is equal to ds by dt. What it is? It is a instantaneous linear velocity. Next, from angular displacement, we know that theta is equal to s by r, or we can write s is equal to r theta. So what happens? Substituting the value of s, we will get it as v is equal to d in the brackets of, what is the value of s? That is r theta divided by dt. So we'll write the equation again as v is equal to r into d theta by dt. What is this d theta by dt? That is the angular velocity, instantaneous angular velocity. So we can write it as omega. V is equal to r omega. So therefore, what's the relation described is that the linear velocity is equal to r is the radius into, what is this? Angular velocity omega. So linear velocity is equal to radius into angular velocity. So this is the relation between linear velocity and angular velocity. Let's define the centripetal acceleration. The acceleration produced in the particle in the uniform circular motion which acts along the radius and towards the center of the circular path is called centripetal acceleration. Let's derive the expression for centripetal acceleration. For this, let us consider a particle moving in a circular path. As you can see in the diagram, a particle is moving in a circular path of radius r, AO. You can see the radius. With a constant speed v, it is traveling, and uniform angular velocity will be omega. Let the particle moving from A to B, as you can see, in time t, and theta will be the small angular displacement made by the radius vector. Next, the velocity at B is resolved into two components, that is v cos theta parallel to AC and v sin theta parallel to AO. Next, we will see when the particle moves from A to B, changes in velocity parallel to AC, we can write it as v cos theta minus v. For small value of theta, that cos theta is equal to 1, what happens? V minus v, which is equal to 0. Next, change in velocity parallel to AO, that is radius, as you can see, AO. We will write it as V sin theta minus 0. For small value of theta, sin theta is equal to 0. What happens is that V theta minus 0, or which is equal to V theta. R is nothing but V theta. So, next we will take the acceleration along AO, which is equal to change in velocity parallel to AO by time. So what is AO? That is V theta. So acceleration, we will write it as A is equal to V theta by T, that is time. So as you know, the angular velocity, we can write it as omega is equal to theta by T. So what happened to the equation? A is equal to V omega. Let's consider this equation 1. Next, we have derived the relation between linear velocity and angular velocity. What is that? V is equal to omega r, or omega is equal to V by r. So we'll substitute omega in the equation. So therefore what happened is that acceleration A is equal to V into V by r. That is omega, we will write it as V by r. So next we will solve it. A is equal to V square by r. So what happens is omega square r. So this we will consider it as equation 2. So this is the expression for the centripetal acceleration. So A is equal to omega square r is the centripetal acceleration. Here completes your chapter motion in a plane. So in the next class, we will continue with a new chapter. Thank you.